All right, so what I want to do here, guys, is go through your entire reactions lab, right? And I'm actually doing something that I have not done in the past, and that is I'm actually going to record myself giving away absolutely every single answer, every single little description to do with this lab report, because a lot of lab reports this time looked either rushed or that people forgot to do parts. Okay, so what I'm doing here is I'm recording this for this purpose. The next time you do a lab report, check it over, okay, with either this one, with this podcast, or with the recording of the day we did the lab. All right, because I think this time, from what I saw, a lot of people didn't listen to the podcast of the lab while they were putting the lab report together. Because if they had, they wouldn't have forgotten the parts that they forgot. Okay, and that's what it came down to. All right, like for example, in the analysis, a lot of people forgot that I told you two gases were produced in the reactions, okay, 1 and 2, and I told you which gases they were. Okay, and a lot of people's reactions were just missing those gases completely. Right? So things like that. Whenever you're putting a lab report together, I'm not saying listen to the podcast then do the lab report. I'm saying do them simultaneously. That way it doesn't take extra time. Okay, so you put one earbud in while you're working on the design, and you listen to me talk about the design. Okay, and you do the design well, then you pause it. Okay, you get that done. You play the part about the hypothesis, get it done. Okay, and then it's not extra time, but it pays off. All right. The other thing is, a lot of people did bring their labs in and have me look them over, and I found, hey, look, you forgot to put in, let's say, your predictions. That was the most common thing to be forgotten. Okay, but if you don't bring it in for me to look at ahead of time, there's no way for me to catch that until I'm assigning you a mark. All right, so there's still those options out there as well. Okay, so for this lab, investigation to chemical reactions, right? The problem on the lab sheet you got was quite long, and unfortunately, a lot of people copied it. What are you supposed to do with it? Right. In your own words, in the form of a question. And quite frankly, it could have been as simple as this. What are the signs of a chemical reaction? That's what we were looking for, was it not? Okay, that could have been the question we were looking for. All right, because really there was no way for us to prove the part about chemical properties. It was just preamble. All right, it was just telling you, look, chemical properties are what determine a reaction. All right, but in the end, the only signs we have a reaction has occurred are temperature change, color change, etc. Okay, so what I put here is what determines if a chemical reaction will occur, and how will an observer know if a reaction has occurred. Okay. All right, our variables. You have to identify them and explain. Okay? This is the last lab where I will write explain beside yours if you forget to do so. Okay? You have to remember to explain. So, the manipulated variable were the reactants for each test. Okay? Why? They're changed by the experimenter in order to observe the effects of different combinations and as subjects with different chemical properties. We want to have things with different chemical properties so that we can see what will happen when we mix them together. All right? That's what causes the responding variable, which is changes in chemical and physical properties. That's what we were looking for as the responding variable. Okay? Evidence of chemical change. Color change, temperature change, precipitates, gases evolved, because this will be different for each manipulated combination as they have different chemical properties, and after each reaction will show their new physical properties. All right? Now, I'm not expecting that yours was that involved, okay? But it needs to talk a little bit about it. All right, controlled variables, temperature of reactants, amount of reactants, same spot plate will be used and will be the same for all tests so as to remove their effects from the experiment and eliminate them as a source of error. I would say that I should have probably said more there. All right, I should have said temperature of the reactants because it could affect the rate at which the reaction occurs. Okay, the same spot plate will be used. I mean, so in case it had any flaws in it or something like that, it would be the same for all of them. So as to remove their effects. Essentially, we want all controlled things to remain the same for every combination. Questions so far? Okay. So that's your first 5 marks. Okay. Restating the problem in your own words in the form of a question and identifying and explaining the variables. Now, for your hypothesis, okay, and I said this in the podcast, the if part needs to deal with what happens in a chemical reaction. In a chemical reaction, do you have new products, new materials at the end? Yes, you do not any longer have the stuff you started with. And if you have new material, those new materials have different what? Properties. Okay, that's the if part. Okay, so if a chemical reaction is the separation, joining, and or rearranging of atoms causing new substances with new physical and chemical properties to be formed, and various ionic compounds, acids, and bases are combined on a spot plate, then temperature changes, color changes, gases evolve, and precipitate should be observed, as these are all signs that the end products are different from the reactants. Okay, I would have been satisfied for 5 out of 5 with something like this. Okay, if in a chemical reaction new substances are formed and various substances are mixed together to cause reactions, then signs such as temperature change, color change, blah, 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 will be observed. I would have accepted that for 5 out of 5. Okay, everybody with me there? If is the premise, and is the experiment, then is what you're going to see if you're right. Okay, always in that order. All right, materials, C sheet, procedure, predictions, those things we wrote down before we went in. All right, and we said we predicted 1 and 2. We knew we were going to predict them wrong. Okay, well we didn't know. Okay, but we predicted them wrong because we didn't predict gases being produced. We looked at them and said this is a double replacement reaction. Okay, so we'll swap the metals and those will be our products. Same thing for pair number 2. We'll swap those and predict the products. Although because I'm a brain, I had predicted right, but we'll leave that. Okay, double replacement, gas evolved. Okay, sodium hydroxide, magnesium chloride, double replacement with a color change. Okay, so these are just the predictions. We don't know, right? Everybody with me so far? Now you didn't have to tell me the reaction type. I didn't tell you to do that, right? All you had to do was just write down the reaction as you predicted it. Okay, then we had to have our observations. Okay, the observations, guys, have to go in the procedure. I still have a lot of people putting them at the end. All right, and quite frankly, several times I gave people 0 out of 3 on the observations, and then later discovered, oh, they do have observations, and I had to go back and change it. Put it in the right order. Okay, people expect things in a proper scientific lab report to be in a certain order. All right, and I showed you guys how you insert the table and things like that. All right, if at the very least, if you were in a total jam and you just couldn't get it into the right place, at least write in the procedure, see observations on back sheet, okay, or 3rd page or something like that, so that I know you actually did it. All right, because otherwise I might just skip it entirely. Oh, well, I got to the conclusion, I'm done. Okay, we don't want that to happen. Make sure it goes in the right order, right? Because that does affect that overall rubric, that very last set of scoring on your scoring chart there. Overall, that's mostly format, all right? Unless you've got a gargantuan amount of spelling mistakes, and I had trouble understanding what you were saying. Okay, for the most part, the overall is just whether you did this in the right order or not. Okay, so observations, this is the chart that you guys could see on my website, right? It's just the same thing. So prior to mixing, both solutions were clear and odorless. Upon mixing, a strong odor and a slight drop in temperature was observed. No clouding or color changes were noted. Okay, it didn't have to be, you know, a big long paragraph or anything like that. It was just before and after, so that we could tell there were differences and thus have a way in our analysis to say, yes, there were new products formed here because after the properties were different. Okay, that's why we want to have the before and after here. Okay, in the analysis, okay, using words and formulae. So you had to do both, and I think in this class everybody remembered to do both. Okay, write the chemical reaction for each pair that occurred in this activity. This is where I was looking for you to have those gases I told you had formed, especially in 1 and 2. All right, so in pair number 1, we had sodium hydroxide with ammonium chloride making ammonia. Okay, NH3 was the gas. Now, how do I figure out what other things are in this reaction? Anybody know? Okay. All right, so this is what we started with, sodium hydroxide and ammonium chloride. And I told you that NH3, ammonia, was one of the products. So here's what we have to do. In order to make this equation work and at the end balance, I need to eliminate these 3 things from the products, or from the reactant side. So this nitrogen, I've taken care of it. And I've taken care of 3 of the hydrogens. Now what's left here? And hydrogen chloride. Is that a double replacement reaction? Now I can figure out what the other products are. Okay, I've eliminated the things that have already been taken care of in the products. Now all I have to do is swap the metals. I end up with H2O and NaCl. Everybody follow? All right. And then the same thing for the last one. We had for the second one, CH3COOH, okay, the acetic acid, plus sodium hydrogen carbonate. All right, and I told you in class that day that CO2 was produced and that the carbon dioxide came from here. All right, so what I do is the same thing I did up there. I eliminate the carbon and 2 of the hydrogens. Okay, what's left is, okay, sorry, that should be Na. NaOH, essentially, and CH3COOH. So this is a plus, this is a minus, that's a plus, OH is a minus, and what I'm left with, H2O and NaCH3COO, or you could have written it CH3CO2Na. Either way would have been fine on that one. All right. This stuff here is sodium acetate. It's the stuff used to flavor salt and vinegar chips. Okay. How did I figure out where everything went? Like I say, I made a double replacement reaction out of what was left. Now here's the thing. Both of these are acid-base reactions. They're neutralizations. What do you always get whenever you have an acid and a base react? Water and a salt. You're always going to get water and a salt. Sometimes you'll get water, a salt, and some gas. All right, but you will always get water and a salt. Do I have water and a salt in both of those? Yeah. In this one I actually have water and salt, okay, like real salt. And this one I have water and a different salt. Remember, salt is a general term referring to any ionic compound. All right? Okay. So that's pair 1 and pair 2, okay, and then we had to make sure that we wrote it out in words as well. You didn't have to write ammonia here, but since I told you that's what the name of the gas was, I did expect to see it quite often, but a few people actually named it nitrogen trihydride, which is also fine. Okay. All right, for pair number 3, we have sodium hydroxide reacting with magnesium chloride to produce sodium chloride and magnesium hydroxide. I don't know how many times I saw magnesium hydroxide written like this. Is that magnesium hydroxide? It is not. I don't know what it is. All right, but it is not magnesium hydroxide. When we have a polyatomic ion, we have to put brackets outside of it if we're going to put another number out there, because MgOH2 is different. This has 1 magnesium, 1 oxygen, and 2 hydrogens. This has 1 magnesium, 2 oxygens, and 2 hydrogens. It's different. Okay? And a lot of people missed the brackets on that one. All right? I'm not sure why. They remembered it on the other ones, but forgot it on this one for whatever reason. Okay? Don't do that on the unit exam. Made up the unit exam. That one's on there. I'm giving away a question on the test. Okay, remember brackets on polyatomic ions. It will be crucial for a 4-mark question on the written response section of your unit exam. Okay, so please be ready for that one. All right, and then pair 4 and pair 5 you didn't have to predict because they involved the phenolphthalein, which when you put in the sodium hydroxide turned pink. And then as you added acetic acid, neutralized back into either neutral or acid and became clear again. Phenolphthalein changes around a pH of about 8 or so. All right, and so it's pink above 8 and it's clear below 8. I think it's 8 something. It's somewhere in there. Okay, which is why it's used to detect the presence of blood. The pH of blood is slightly basic actually, and so when you hit that stuff, it turns pink. All right. For pair number 6, we have potassium iodide reacting with lead 2 nitrate, and that's a double replacement reaction producing lead iodide and potassium nitrate. All right, and that one also produced a precipitate. Okay, and you can see here written out in words. Okay, we've got the little Roman numerals in there for lead. And then for pair 7, I saw this one, it was weird. I saw this a bunch of times as well, okay, where we had HCl plus zinc, and then people did this. Is hydrogen special? Yes. And what's the charge on zinc? 2. I don't know how many times I saw people forget to drop and swap zinc chloride. I'm not sure why that happened, because people remembered to do it for lead 2 chloride, and they remembered to do it for sodium or for magnesium hydroxide. Even if they didn't do it right, they remembered to do it. Okay, but for some reason, people forgot to swap and drop a lot, often, on zinc chloride. I'm not sure why, but it should be ZnCl2, and this should be H2 over here. Okay, which means a 2 there balances everything off. Okay. So just, I guess the point I'm trying to make here is take your time. Don't forget to do the easy things that you're really good at, okay? Because they'll help you with the harder stuff. All right, then question number 2. Big problem with question number 2. People not actually identifying the precipitates. They said precipitates formed in reactions 3 and 6. But then didn't tell me what the precipitates were. That was the point of the question, was to tell me which of the products in those reactions were not soluble. So if we go back to pair number 3 here, and we look at our solubility chart, do we really need to look at our solubility chart, or do we know that sodium chloride is soluble in water? Yeah, this is soluble in water, so this was the precipitate. Okay, so we needed to say in question number 2, magnesium hydroxide is not soluble in water. All right, and the same thing for pair number 6. Okay, we look at our products here. We know that all nitrates are soluble. Right, it says that essentially on our solubility chart. So lead 2 iodide must have been the powdery yellow stuff. Okay, everyone follow? All right. So that's what we've got written down here. Okay, I wrote out the reaction. This reaction was a double replacement reaction, and after checking the solubility chart, it's found that lead 2 iodide is not soluble and was thus the yellow precipitate. And the same thing for number 3, okay, that magnesium hydroxide is insoluble and the precipitate observed in the reaction. All right, for your conclusion, you restate your hypothesis and using your observations explain why you accept or reject it. So I italicized my hypothesis. Okay, I'm not going to bother reading it again. Okay, and then here's my justification. Upon examination of the data and observations obtained in this lab, notably the presence of color changes, evolution of gases, formation of precipitates, and temperature changes in many of the reactions, this hypothesis can be safely accepted. All right, I said this was going to happen. I said these would be the signs. Here they are again. They were observed, thus I can accept it. Okay? This is because anytime the above indicators were present, the final products had different physical and chemical properties from their starting materials and had thus undergone a chemical reaction. All right? So I'm re-explaining. Here's what a chemical reaction is, and this is why I can conclude that they happened. All right? But I did have a lot of, this is acceptable because I saw the stuff happen. All right? Which isn't going to get you 4 out of 4, okay, on a conclusion. All right, we just need a little bit more detail than that. Okay, sources of error. Spot plate used was white, and actually when we originally did this lab, we actually still used the little depression plates, okay, to do this lab in, making it difficult to see any white solids that may have been present in the reactions. To improve this, a transparent spot plate could be used so that it'd be easier to see all colors of solids, which of course we did. Okay. Very small amounts of reactants were used. This may have made it possible to miss the evidence of a chemical reaction because the indicators may have been too small to notice. To improve this, larger amounts of reactants could be used in future investigation. Well, I've taken those two things into account and already done that for you guys. So sources of error for you could have been that your rinse bottles may have, again, accidentally been filled with tap water. Right? That could have interfered with the reactions. In fact, it could have caused small amounts of precipitates to form when they shouldn't have. All right? I didn't see any evidence of that in anybody's lab, but it could have happened. All right? You could still use the small amounts of reactants. That, even with the amounts we use being larger than before, it's pretty hard to get a significant temperature change from that small of an amount. Right? And that could have been a source of error as well. Okay? I was generally accepting of any sources of error as long as they weren't, yeah, we didn't do that very well. We should do it better next time, because that's human error. Do it better now. Okay? If you know you didn't do it right, do it again. Okay? All right, the class discussion stuff. So this you'll want to write down. okay? Because this is the stuff you didn't have to do but is on there and oftentimes comes up on unit exams and stuff. Okay, what evidence did you have that a chemical reaction occurred in each pair of reactants? Essentially, it's just restating your observations. Okay, we know that there was bubbling in 3 of the reactions. Okay, and so that would have been in the vinegar and baking soda. Okay, in reaction number 5, there might have been a little bit of bubbling as you added the acetic acid to the sodium hydroxide and phenolphthalein. I didn't notice that it happened very much for you guys this time, but it has happened in the past. Okay, and obviously number 7, when you put the hydrochloric acid on the zinc, okay, it bubbled a lot. All right, what gas was being produced there? Hydrogen gas. In fact, if you capture that, if you put a beaker over top of that reaction as it occurs, okay, the hydrogen gas will collect in there, and you can blow it up. Okay, if you actually just put a burning candle or a splint over that reaction, the flame jumps continuously as it burns off the hydrogen gas. Okay. Okay, obvious color changes, pairs 3, 4, and 5. Okay, and 6, obviously the yellow. Okay, so in pair 3 we got a white precipitate, so that was a color change. 4 and 5 were the phenolphthalein changing from pink to clear, and 6 was the yellow precipitate there. Okay, some reactions had temperature changes, 1, 3, 5, and 7, very small. Okay, while in a few precipitates were formed, 3 and 6. Okay, did all groups witness the same changes? Were everybody's observations the same? The only thing that sometimes is different is the temperature changes. All right. Once in a while, some people don't register the change, or for whatever reason, or they had a little bit more than somebody else, or a little bit less. So the only thing that really does tend to be different are the temperature changes, right? And what's that caused by? The amount of stuff you use, right? And how concentrated I make the stuff. This time I made it really concentrated, so that wasn't really going to be a factor. Okay, compare your predictions with the actual changes you observed. Which of your predictions were false? Well, obviously, we were false on 2 of the double replacement reactions that didn't end up being double replacement reactions. Okay, was there any way for us to predict that a gas would be produced in those reactions accurately? Not really. I mean, from what I've taught you, you would say, oh, it's 2 ionic compounds, it's a double replacement reaction. Okay, I set you up. I'm sorry about that. Okay, but okay, sometimes that's how science works. We want to be wrong in our predictions so that we can figure something else out. Okay, learn something new. All right, and a lot of times we have that a lot of people predict that HCl would not do anything with a piece of metal. All right, but in this case, zinc is what we call an active metal, and it reacts violently with any acid and produces hydrogen gas quickly. Okay. All right, questions on that? Okay, if you got questions about your